All right, so we want to be constructing a square matrix, size n by n, where n is the number supplied here, so the argument of the function, the input. And basically, it's got to contain all the integers from 1 to n squared, or n times n. So like, for example, if n is 3, we want 1 to 9. If n is 4, we want 1 to 16, etc. And basically, the idea is we want these to be sort of forming a spiral. We want them to be in a spiral order. So we want to start right up top here at the 1, and then basically just move around until there's no room left, like until we can't go any further. So we've got, I guess there are only 3 tests here, which, well, that's not very many. If we look at the second test here, so if we look at this, we notice like it goes around. They're sort of like levels to this, depths to this, and we'll take a closer look at that pretty soon. But before we do, I want to talk a bit about how we're going to approach this task. So the sort of typical way, and we will look at this eventually, but the typical way is to basically start with the 1 here, go as far as you can, and then once we hit the boundary here, once we hit a wall, so to speak, we're going to switch directions. We're going to turn to the right, or yeah, if it's an aerial view, we're turning to the right. Anyway, the point is we're going to turn clockwise and then keep going as far as we can. Basically, just keep that process going. That's going to be sort of the idea. But I was thinking about it. I was thinking, well, what if we don't want to change directions? What if you know, we get to the end here and we don't want to go down anymore? We just want to keep going to the right every time. Let's say we always just want to go to the right. So how could we accommodate that? How could we make that happen? Well, basically we could say, all right, put the 1 here, put the 2 here, put the 3 here, and then we hit a wall. We say, okay, well, there's nothing, no other elements beyond this one. We can't keep going to the right. So in that case, we could just take this whole thing and just rotate it, you know, just rotate the entire matrix we've come up with so far, and then just keep going to the right. You know, it would be like, here's the 1, here's the 2, here's the 3, and then we would just put the 4 over here, put the 5 over here, and then we'd rotate it again, etc. Ooh, jumpy mouse. Okay, the point is, that's what we're going to start with. So I was thinking about this, and I was thinking, well, you know, we could just like create a matrix and then make like a function for rotating that matrix and sort of do it that way. But then I was thinking, well, wouldn't it be kind of nicer if the matrix was sort of its own kind of thing, its own kind of object, where we could just tell it, okay, now rotate, you know, tell it to rotate, as opposed to getting like an outside function to modify it. And I kind of liked that idea. So that's what we're going to do this time. We're going to use an object, and I guess we might as well start with that. So we'll do a bit of a constructor here. So we're going to say function spiral matrix. And what input is it going to take? I guess size. You know, it's going to be a spiral matrix of a particular size. So we'll give it that property. That size is assigned the value of size. This is a lot like task 57, where we used a lot of objects there. We're making linked lists and stuff like that. This is the same sort of thing. So we're creating new objects here. We want to give it some properties and eventually some methods. So we're going to have kind of like a position in our matrix. So specifically, that's going to take an x and a y value. So I'm going to say this dot x is assigned the value of 0. This dot y is assigned the value of 0. They're going to start at 0, 0, because that's basically where we're going to put the first element. Speaking of which, let's call that num. This dot num is going to start at 1. And this dot matrix. This dot matrix is going to start out as just this empty array sort of thing, and we want to fill it up. So we'll just start by doing this in a pretty traditional way. We'll let I be assigned the value of 0. We're going to let it increment all the way up to n. And for each I, we're going to start a new row, which we're eventually going to push inside the matrix. So the matrix is just going to get that row. And what's going to be in the row? Do another variable here, j. It's also going to go to n, and j++. I guess maybe instead of n, let's make that this dot size, just to be sort of consistent with what we have above. And the other thing about this is, we could sort of take all this and actually remove it from our spiral numbers here. And that, yeah, maybe that would be better. It's kind of a standalone thing, and we'll make reference to it down here pretty soon. But for now, yeah, it's just going to stand on its own. So we'll have this dot size instead of n, because n is within the spiral numbers function. It's not within the scope of what we have out here. Okay, so then for this part here, basically we just want to say row dot push, and we're going to start with just zeros. We're just going to make these all zeros. So basically now, well, let's actually test this out. So we'll say let spiral be assigned the value of new spiral matrix with a size of n, and we just want to start by returning spiral dot matrix. That's pretty much it. And it says matrix is not defined. Okay, so why is that? We've got this dot matrix right here, so why would that be not defined? That's kind of strange. Line 15, matrix. Oh, you know what the issue is? This dot matrix. Okay, so specifically since we're talking about the one belonging to whatever particular instance of the object we're using here, we've got to put the this in there. So keep in mind, over here I'm saying let spiral be assigned the value of new spiral matrix. So basically when I do spiral dot matrix, it's replacing this basically with spiral. So like when it goes through this whole thing in the constructor, instead of this, it's saying, okay, so spiral.matrix.push row, spiral.size, etc. So let's try running this one. We'll see if that works. And there we go. Okay, so it's the right size. It's all zeros right now, but it's the right size. Yeah, okay, so this is looking good. We've got kind of a blank canvas now. And basically we wanna work with that. So we basically need two other methods here. We need one that's going to place the numbers. So this dot place num, I guess we could call it. It's going to be a function. I don't think it needs to take in any inputs, and it's going to do stuff. So basically it's going to place the number. And we also need one called rotate. And this is basically just going to rotate the matrix. Again, I don't think we need to really give it an argument. It knows what to do. And then, okay, so basically the idea is we want to place the numbers as far as we can. So, okay, let's start with this one, the place num, and then we'll talk about how we're going to do rotate. So basically place num, we're going to start with some coordinates. Now, I mean, our coordinates are basically these, like this dot x, this dot y. I want to simplify this a little bit, so just for the purpose of simplicity, I'm going to say let x and y be assigned the value of this dot x and this dot y. So I'm using a destructuring assignment there. That's basically the same as saying let x be assigned the value of this dot x and let y be assigned the value of this dot y. So we could do that in 2 lines, but hey, might as well be efficient about it, right? So this is a nice ES6 thing. It allows us to assign multiple variables at a time, which is really nice. Okay, and then basically we want to say this dot matrix at x at y is assigned the value of this dot num. And then we want to say this dot num plus plus, increment it, right? So we've placed it, we've laid down the number, we're now incrementing the number. The next thing to do is basically to find the next position, our new x and y values. So at that point, we basically want to say, well, can we just keep moving to the right? Like we'll put the 1 down right here, and then we want to say, yeah, can we move to the right? And yeah, we'll be able to put the 2 here, put the 3 here, put the 4 here, put the 5 here. It's once we get to the 5 that things get a little more interesting. So at that point, what we want to check for is number 1, is there anything to the right? If we were to increase, I guess what we would call the y value here, because it's our second argument, if we were to increase that y value, would it go off the page? Would it exit the matrix here? Would it be out of bounds in that case? Or would it be encountering something where we've already filled in a number? Like, for example, if we were at the point where we had, like, let's say the 19 here. So there does exist another entry here. We have the indices to have another spot here, but there's already something there. It's not a 0 there, so we actually would want to rotate in that case and keep going from there. So basically, at this point, what we want to check is if y plus 1 is in this dot matrix at 0. Okay, so this is kind of a complicated line right here. I want to make sure this is all making sense. So let's break it down one step at a time. First of all, the y plus 1, I'm basically just saying if you're moving to the right, we're incrementing y. We're increasing it by 1. So that's the y plus 1. In basically is checking to see if this number is one of the indices in this array over here. And this array specifically is the first row. Now you might be wondering, well, why don't you use like matrix at x? Wouldn't that be better? And yeah, it could, for sure. But the thing is, they don't have like a different number of elements on any of the rows. I mean, we don't even technically need to even put in the 0 here. We could just say in this dot matrix because we have the same number of columns as we have rows. And so it wouldn't really make much of a difference, but I just want to make sure it's kind of accurate, right? So matrix add 0. And add 0 because they're all going to have a 0th row, and it's going to be the same length as all the other rows. So without loss in generality, this is going to work for every one of them, or at least it should. I guess we'll find out if it does. And what else do I want to check? Well, this is an AND. So the only situation under which it'll get to the second part of this AND, like the statement I'm about to write in here, is if this is already true. Because if this was false, it wouldn't bother checking the second part. It would say, oh, well, no, why would I bother with that? That's false, so obviously the whole thing is going to be false. I don't need any other information. Whether or not the second part is true makes no difference. The whole thing would be false. Okay, so then basically what I want to check is this dot matrix at x at y plus 1, and keep in mind that must be within range, right? Because we already checked that y plus 1 is within the range of values we're looking for, so this must exist. This isn't going to be like a null or something like that, but we want to check if it's equal to 0. Okay. And basically if it is, then that means, well, we can just increment y. Just increase it. Just go 1 to the right. So maybe I'll make a comment for that. Go 1 to the right. All right, and then otherwise, if you can't go any further, let's rotate. So we'll say this dot rotate, and then we are actually going to increment y after rotating it. So basically the idea is kind of like, you know, we get to this, whoa. Okay, so we get to this point over here, and we can't go any further to the right. You know, let's say we've already placed the 5 here. We can't go any further to the right. So we're going to say, okay, well, let's rotate it, and that will mean, you know, like this value goes to here, this value goes to here, etc. This one that we were at is going to be over here, but keep in mind there's already 5 there. We want to actually move it to the next one where we would then put the 6 afterwards. So keep in mind that's what this part's doing over here. That's why we need a y++, because we don't want to refill this one. We want to move on to the next one. So with that in mind, I guess we could restructure this here. Like we could actually, because I'm noticing now we're doing this dot y++. So like one way or another, we could probably take that out of the if statement and actually just make it like if not this, then rotate it. Otherwise, do nothing, I guess. Maybe we'll take a look at that afterwards. Let's just make sure this is going to work first of all. Here, let's test it. We'll do spiral.placeNum. See if that works. Hey, it's placing the 1, so that's pretty good. And then we'll see what happens if we put a couple more of these in here. PlaceNum, PlaceNum, PlaceNum. Okay, so we get the 1, the 2, and the 3 over here. We get the 1, 2, and 3 over there. Good. And so now I'm going to try this one, and what we're going to find is something weird's happening here. The 4 just went right to the next element there, which really should not have been an element. So why is that happening? Well, it's because it's doing this dot rotate, and it's saying, okay, this dot rotate, it's a function. What does it do? Oh, it does nothing. Okay, so we want it to do something, so let's make it do something. So specifically, we're going to start by doing this. We're going to say let b be assigned the value of this array, and this is going to be like our rotated matrix, basically. Okay, so we're going to say for let I be assigned the value of 0, I is less than this dot size, I plus plus, And we're going to do something similar to what we had before. We're going to have a row here for let j be assigned the value of 0. J is less than this dot size as well, j plus plus. And then before, well, let me just get this in here. Actually, it's not this dot matrix, it's b dot push row. And I guess we'll just put a little bit of extra space in there. Inside the for loop, we're going to have something a little bit different now. So instead of row.push 0, like we had before, we're going to say, well, let's push something in here that comes from the matrix, this dot matrix, and specifically, we're going to take, it's not going to be I and j. Instead, we want to rotate this thing. So we're going to use j. So what was... okay, so basically we're saying the column of this thing, like whatever we're going to put in the column, it's going to be whatever the row was of the previous one. And whatever the column was is going to become sort of like our row here, except a bit different because we basically want it to rotate this way, right? So the 3, this was 0, 1, 2, column 2. We actually want it to become row 0. So we're going to do basically the size minus 1 minus I. That's sort of the idea here. So this dot size minus 1 minus I. So it's basically the idea, okay, we're not just doing ji, we've got to do this minus thing. And the reason is because if we just did j followed by I, we wouldn't be actually rotating it, we'd be reflecting it like along a diagonal. That's the idea. So like the 2 would go over here, the 3 would go over here instead. We don't want that happening, so that's why we sort of invert this dimension here. Okay, so that's rotate, and then what we'll do at the end is we'll say, well, this dot matrix is assigned the value of b. It's just going to take on this new matrix that we've created, which is the rotated version. And in fact, I don't like this b here. Let's just call this rotated, just to make it a little more clear to the reader what we're actually talking about here. So there we go, rotated, rotated, cool. And then one more thing we need to do is basically just adjust the coordinates because those also are rotating. So they're going to be, okay, we're kind of assigning it in a different order now. So instead of saying like, instead of saying like row at ij is going to be matrix at j size minus 1 minus I, instead we're saying our new coordinates are going to be the rotated version of whatever we had before. So we're kind of looking at it from the opposite perspective now, which is why it's going to be basically the same thing, but kind of the opposite. So we're going to say this dot size minus 1 minus this dot y for our new x value, and basically just this dot x for our y value. There we go. So that's our rotate function. Let's see if that's working. So we'll try running this, and great. Yeah, awesome. We got the 1, 2, and 3. The 4 is in the right place, and you'll notice the matrix has been rotated. So, okay, cool. Pretty not bad. Let's try doing this a bunch more times. So we do want to do this place num thing, but for how long? Well, basically we want to say for, or actually, you know what? We can just do it this way. While, do a while loop, and we'll say while spiral.num is less than or equal to n times n, because that's basically how far we want to go, right? I mean, it's the square of the number that's going to be the last one. So as long as it's within that range, as long as it's not greater than like 9 or 25 or whatever it happens to be, we can keep placing numbers, and we will keep placing numbers. So let's try that. Okay. So if we look at this, we sort of have like 1, 2, 3, 4, 5, 6, 7, 8, 9. It is spiraling. That's good. And if we look at this one, yeah, looks like it's spiraling. So that's awesome. That's what we want. The thing is, it's not really in the right orientation here. You know, like we want the 1, 2, 3, 4, 5 to be like the first row. Whereas right now it's kind of a column going upwards. So we sort of want to rotate this back into place. Or I suppose we could also just put it here, like, you know, say, like if, Like if the number is less than n times n, then do this rotate. If it's not, don't do the rotate, something like that. But you know what? I'm just gonna adjust it here. So rotate into the final position. So we'll say spiral dot rotate. And how many times do we have to do that? So I don't think 1 is going to be enough. Yeah, that's sort of upside down. We need it 2 more times. So we'll say for let I be assigned the value of 0, I is less than 3, I plus plus, spiral.rotate. Let's try that and we'll see if that works. And while we wait for that, let's just clean this up a little bit. Ooh, oops. Yeah, okay, so that looks like it's working. Very nice. Very nice. Okay, cool. This is great. Let's see, are we ready to submit this thing? Yeah, I don't see why not. Let's submit it. Oh, incorrect. I wonder why that is. Well, maybe we can take a look at some more tests. So we have one for an n value of 3, one for an n value of 5. You know what? We're not looking at any that have like an even number of digits, or an even size, I should say. So let's try that. And for the output, I'm not actually going to spend the time putting in the actual expected output here. Let's see. Okay, so notice the 1 is not starting in the upper left corner here. It's kind of opposite. So I guess, you know, it has to do with the fact that we sort of finish differently. Like 16 isn't right in the center. This doesn't have an extra layer to go through. So I guess it sort of depends. It's not necessarily going to be 3 here. It depends on the value of n. So let's say that. So we'll say is n even or not? So basically, if n is odd, we want it to rotate 3 times. If n is even, we want it to rotate 1 time. Let's try that. We'll see if that works. Gives us a better result here. Good. This one's working good, I think. Yeah, looks good to me. And are the others still working? They are. Okay, so let's try submitting that. We'll see if that works. And there we go. Okay, nice. So that's good stuff. Feels good to have that one. Oh, hey, thanks. But no, not right now. Yeah, feels good to have that one done, but I think we can probably make it a little bit better. The first thing I want to address is this, because we pointed out that, you know, we're doing this .y++ like regardless. So let's see if this works. Do nothing. Do nothing. And else rotate. Is that still going to work? Yeah, seems to be working. I know it says 2 out of 3, but it's because I didn't actually give this the right input. So, okay. That's, I guess, a little better. We could make it better than that, too. So, you know what? I'm just going to take all this and just say not. If not that, rotate it. And yeah, I like that a little better. That's better. Okay, cool. So that's good. Now, there is one other thing that's kind of bugging me about this. So I'm looking at this thing and I'm thinking, hey, this is pretty cool. It's working nice. But I have an issue with it. So the first issue, I have a couple issues, but the first issue I have is, I don't know if this would work if we had something like really, really big. Like, for example, let's give it an input of like 500. And I don't think we really need to worry about this, because if we take a look at the description here, we're not going to get anything above 10. So I think 500 is maybe going a little overboard, but notice it says output limit exceeded. And actually, maybe that's not bad. Output limit exceeded. That doesn't mean that it timed out. It just means this thing's too big to show. So, okay, it can handle 500. That's actually kind of surprising. Let's see if it can handle 1,000. No, I'm curious. I'm just wondering if it's going to time out or not. Okay, so now it is timing out for 1,000. Now, I think part of the reason for this, anyway, is when we look at the way we're rotating this, we're creating a new matrix. So we've got this new matrix. It's called rotated. We're going through every step of it, and basically we're creating a whole new matrix in memory every time we want to rotate it. Now, if we think about the size of this thing, whoops, wrong thing. If we think about the size of this thing, basically every row is going to have 1,000 elements in it. And let's see, if it's going to be a 1,000 by 1,000 square matrix, that's 1,000,000 elements. So every time it needs to create rotated, every time it needs to rotate, and I mean, keep in mind, if it's 1,000, like it's going to have to do that a whole bunch of times, like 4,000 times or something like that. And so for every one of those times, it needs to create a whole new matrix with 1,000,000 new elements. Like that feels like it's a lot to be storing in memory. So I want to try to alter this. That's the next thing I want to do. It is kind of bugging me that we're creating a whole new matrix in there, and I want to see if we can do it in such a way that that just has us actually like rotating it in place. So not creating a new matrix, just changing the elements in the current matrix so that they're rotated. Okay. So that's a little trickier. How are we going to do that? Well, basically, if we look at this example over here, we could say, and I'll get my tool out. So what's a good color for this? Yeah, there we go. Okay, so basically, we'll start with the 1, and we kind of want to say, well, if we're rotating this, we want the 1 to end up over here. We want the 3 to end up over here. We want the 5 to end up over here. And we want the 7 to end up over here. The thing is, one of those is going to get overwritten in the process. So we probably want to have some sort of temp variable. So maybe we'll say, temp is assigned the value of this. And then this is going to get assigned the value of 3. The 3 is going to get assigned the value of the 5. 5 is going to get assigned the value of the 7. And the 7 is going to get assigned the value of temp, because we have it stored in there. So that's basically going to be the idea. Once we're done that, we're going to move on to this element and do the same thing. So we're going to rotate it. We're going to say, okay, well, this is going to go over here. This should go over here. This should go over here. And this should go over here. So again, we're just sort of spinning it around. And that's honestly pretty much it. That's pretty much all we're going to have to do for this one. But it's going to get more complicated for something like this. Let me try to expand that. Yeah, for something like this, it's going to get a little more complicated because, yeah, we want the 1 to go where the 13 is, the 5 to go to the 1, etc. And then we want to sort of do the same thing with the 2, with the 3, and with the 4. So we want to get the 1, 2, 3, and 4 there. Next, we've already dealt with the 16. It would have been like the 4 went into its place, the 16 would have gone into the 12's place, etc. But we haven't dealt with the 17 yet. So basically the 17 needs to go where the 23 is, the 18 needs to go where the 24 is, and I guess the 25 doesn't really need to do anything. But basically what we're seeing here is, and actually I'm going to switch over to my whiteboard because I preloaded this matrix in here. What we're seeing is that we're doing something like this. We're kind of taking this triangular slice of it where we're going to say, all right, so we need to look at all of these elements. Have I gone too far there? Because I don't think, oh no, it's erasing everything. Okay, I don't think I need to go as far as the 49, right? So, but is that going to accommodate the 42? Let's see. Yeah, I guess it's like, is it kind of all these elements? Or is the 29 going to be taken care of? Yeah, from the 25. So, okay, it's not even that. It would be like all these elements. I think that's about right. Yeah, I think it's all of these elements that we need to change. Right, so the 1's going to go over here, 2 is going to go over here, 3 is going to go over here, 6 is going to go where the 24 is. From there, the 25 would go to the 37, the 26 would go to the 38. Where's the 28 going to go? It's where the 40 is going to be. Yeah, so this would be enough. So basically, we want to basically cover like kind of a quarter of the matrix. It's like one sector of it, and then for each one of those we're sort of modifying 4 values at a time. That's kind of the idea. Okay, so what are we covering on each row? So if our row is let's say row I, then we want our J to be going from, I guess, I, so 0, 1, 2. So it goes from I all the way to kind of like this dot size minus 1 minus another 1, I guess. And then minus I on top of that. So basically, it has to be strictly less than this dot size minus 1 minus I. So it's going to go, J is going to go from I to this dot size minus 1 minus I. Yeah, that's the idea. And then where's I going to go? Well, it's basically going to go from 0 to this dot size divided by 2. That's sort of the idea. So let's do that. We're going to, I think, basically just change everything except for this thing. I think that's still good because that's the thing that puts our position, rotates our cursor, so to speak, right? It rotates our position. So just for the sake of simplicity, because we're going to be making reference to this dot matrix quite a bit here, and I don't want to have to type out like this dot matrix, this dot matrix, this dot matrix. So I'm just going to say A. A is going to be assigned the value of this dot matrix. Now keep in mind, you might be looking at that and thinking, wasn't the whole point of this to avoid having a second matrix here? And yeah, it was. But the thing is, this is not creating a second matrix. This is just creating a new variable that's pointing at that same matrix. So it's not like we're making a deep copy or anything like that. I'm coming up with another name to refer to this matrix as. And it's just for the sake of simplicity. Okay, so what we found is for let I be assigned the value of 0, I is going to go all the way to this dot size divided by 2, not including. And what else? We're going to have J in here as well. J is going to go from I to this dot size minus 1 minus I, J plus plus. There we go. So that's basically, these are the boundaries that we found over here for our slice over here. Let me know if you have any questions, comments, or concerns about that. But basically this thing here, this loop, is only going to cover this sector of our matrix. And keep in mind, like for this one, it's basically just going to be this. Technically, it'll include the 9 too, but it's not really going to make much of a difference. Or will it include the 9? I'm actually not sure. Yeah, I think it will, because this dot size would be 3 in this case. Divide that by 2, we have 1.5. 1 is still less than 1.5, and 1 would be the row number, or the row index over here. So yeah, that works. Okay, so what do we want to be doing with this? Well, like I was saying, first of all, we want to have a temp variable, and it's just going to be our matrix at I at J. So this is where it's nice having this A value here. Otherwise, we'd have to do this dot matrix at I at J. It just looks a little more hectic. Okay, and we're gonna say we're gonna have this X and Y. It's not gonna be the same as this dot X and this dot Y. I just sort of want to have this for again, kind of the sake of simplicity. All right, there we go. So X and Y are gonna start out as I and J. And basically, I'm going to say for, I guess we'll say K be assigned the value of 0, K is less than 4, K plus plus, and then what do we want to say here? Well, we're going to let next X and next Y be assigned the value of Y, and this dot size minus 1 minus X. Okay, so that's that same rotating thing we were looking at before. We're taking whatever the Y value was. So let's say we were talking about this right here. Okay, so that would be X value of 1, Y value of 3. And we basically want to rotate it to this one here where our X would be 1 and our Y would be 1. So is this actually doing that? Let's find out. So we found that the Y value here was 3, right? Wait a sec, is this right? Yeah, the Y value was 3 there. Oh, am I not doing this right? Oh, yeah, okay. Sorry, I'm rotating in the wrong way. So I'm actually rotating clockwise here, just to get to the next one here. And we'll see why we're doing that in just a sec. So basically, okay, so we start with this one. This was X value of 1, Y value of 3. When we switch it up, we're going to say now the X value, the next X, is going to be Y, so it's going to be 3, X value 3, so we're on the third row. And what's the Y value going to be? Well, it's going to be this dot size, which is 5 minus 1, so 4, minus X, which is 1, 4 minus 1, 3. So 3, 3 is where we end up. It's the 21. So we're rotating clockwise. Now, the reason we want to do that is because we're saying, okay, so that's going to be the next one. What we're going to do is actually assign this, we're going to assign it the value of 21 there, right? So we're going to say a at x at y is assigned the value of a at next x next y. Okay, so in other words, whatever we have at this indices or these indices, we're going to replace it with the value that we have at the next spot. That's basically the idea. Okay, so that's why we're rotating clockwise, even though what we ultimately want to be doing is rotating the entire matrix counterclockwise. Yeah. Okay, and then basically if I is less than 3, so if not I, k. If k is less than 3, we know it's going to be less than 4, but if it's less than 3, if it's before the final value here, we'll say xy is going to be assigned the value of next x, next y. We're going to actually move it on to the next one. Now, why are we not moving on if we get to the end here? If we get to our last value there, the reason we're not going to move on, so let's say we were starting with 17, right? We've stored 17 as our temp value, and then we said, okay, so the next one is going to be this, 17 is now going to be 19, the next one after that is this one, so 19 is now 21, the next one after that is this one, so 21 is now going to be 23, and then, well, actually now k would be 3, so we're not going to get the next one there, and the reason is because now we want x, y to point to this one, so we can say, now replace that one, a at x at y, with temp, because it's the value that we stored from the beginning to put there. Because we've already overwritten 17. 17's already been replaced with 19. 19's been replaced with 21. 21's been replaced with 23. So really, like we would have a 23 here, we'd have a 23 here. We don't want both of them. We're going to replace this one with 17. 17 is no longer in the matrix, but thankfully we stored it in the value of temp. So that's what's going on with that. So basically, our rotate function is now just modifying the matrix, sort of one element at a time, or kind of more like 4 elements at a time. But the point is, it's not creating a new matrix. It's keeping this matrix in place and just modifying its values. The question is, does it work? Let's find out. Hopefully. Okay, so I know this might be a little bit alarming here. It's still, it can't handle that one. Maybe not too surprising, but it is passing. In fact, maybe I'll just clear that one. Whoops, clear that one as well, confirm. Let's just make sure that it is passing these tests. Okay, so that's good. Let's see if it's passing all the hidden tests as well. It is. Okay, so that's good. I like that a little bit better. I feel better about the idea of rotating it in place as opposed to creating a new matrix every time, because yeah, it could be pretty costly if we had some pretty big values there. All right, so this is looking pretty good. I'm happy with this, I would say. Let's see. I guess maybe we'll make another comment here. Fill in all the numbers. Yay. Okay, and then here's what I love about this. This final line here, like when you can do stuff like this, oh, it feels great. And specifically what I mean is, look at how semantic this is. I was like, should I put in a comment here? And I thought, well, why would I? Return spiral matrix. I don't think that could be more clear. So that's a nice thing about objects, like spiral dot matrix. It's kind of a cool way to be able to just write it out. It's very clear to the reader what this means without even needing to put a comment in here. So I feel like this part of the code here, it looks really clean, it looks really succinct, but it relies on having this spiral matrix object. It has to already know what this spiral matrix object is. And we might be looking at that and thinking, well, kind of overkill. Doesn't it seem sort of like overkill to have this like big old constructor for something that we're really only using one of, and we're really only using it in this one problem? Like, if it turned out that spiral matrices were stuff that we needed to see in lots of other contexts, and like there were lots of other problems where we would use them, or maybe we're doing a web app where it's like a really important part of it, like I don't know, it's kind of some kind of game or something like that involves it, then yeah, we would want to have something like this. Like if there are going to be multiple spiral matrices, then that would make sense. But I'm thinking this does sort of seem like overkill to me. I think what I want to do is take all this stuff, get rid of that. I want to put it inside here, and I'm going to have to adjust the indentation. So there we go. And I basically want to say, well, instead of this, I just want to say, let spiral be this. I'm just going to use an object literal. So it's going to be an object, and we're going to sort of define it a little bit differently. So first of all, we're not going to deal with size anymore because we've got n. We're inside the function now, so we don't need this dot size. We can just make it n. All right, so there's going to be a few of those to replace. This dot size over here, this dot size over here. I'm just going to highlight size and see if there are any others. There's that one down there, and I guess that's going to be the last one. So n and n. Okay. But now we've got a few other problems here. The first thing is, like, this is not the right syntax for just defining an object literal, a JSON. So there, we want something more like that. Actually, not even like that. We want something more like this. Okay, there we go. So x, 0. Okay, we use colons and commas for our objects. So x, 0. Y, 0 with a comma. There we go. Num is going to start out as 1. And now this is where things get a little trickier. So we want to say that matrix is going to be this thing, and we'll move on from there. But the problem is now we just sort of have this arbitrary code right here, right in the middle of our object. So we'll deal with that in just a sec. There are basically 3 ways we can deal with it. I'm just going to cut it for now, so Control X. Because I want to just get these guys in before we go any further. So we want to say rotate, and we can just do something like this. So it's going to be a function, and we can still do these. We can still say this dot matrix. In fact, it's kind of important that we do, because otherwise what matrix are we talking about? And then let's see, is there anything else we need to change in here? I mean, all of this is are okay. We want a comma at the end here, and then we want to make this place num colon function. Okay, cool. And that's getting a little wide there. So, okay, that's better. And yeah, I guess that's the final element. Now, we could technically put a comma in here. Some people have been talking about like that being a good practice. Like you should put a, what do they call that? A trailing comma, I think it's called. But I'm not sure. I don't usually put them. I don't know if that's bad or not. Let me know, if you got the intel on that. I'd love to hear it. But as for now, okay, we almost have this under control. The problem is if we try to run the test, it's going to be like, well, what are you talking about? There's like, this is an empty matrix, man. You need something better than that. So here, we're going to get this out here. Let's just say, I guess, so let m be assigned the value of this empty thing, and not this dot matrix. We're just going to say m dot push. Okay, so we've got this m thing. And could we do it like this? Could we just put m in there, starting out as this 0 full matrix? And the answer is yes, that's going to work for us. So, okay, that's good. That's getting a bit better. But I kind of don't like the idea of like making this matrix and then putting it inside this object here. I don't know, maybe that's better, maybe it's not. I'm not really sure. But the point is, I think we can do it at least a little bit differently. So we're going to use something called an immediately invoked function expression. I think it's called something like that. But basically, it's also, I think, known as a closure or a singleton. This is considered a pretty big part of JavaScript, and it's something we haven't really talked about much at all. I think we mentioned it like a while back, like in one of the earlier videos, but it's been a long time. So basically the way this is going to work is we're going to make a function, and then we're going to call a function. Well, we're going to make a function and then call it right away, basically. So let me put it this way. Let's say we'll make this a function. We'll say function do matrix, and it doesn't take any inputs, and it's basically just going to be this right here. It's going to be all this stuff. So we're going to say let m be assigned the value of this array. We're going to give it rows that are going to be full of zeros, and then at the end of this we're going to say return m. Okay, so now we can say matrix. Oh, well, it's just going to be do matrix, and specifically we're going to call do matrix. Notice the parentheses here. The reason is because if we don't have that, if we just say do matrix and we're not calling it, then it's going to say, okay, so matrix is this function. as opposed to saying, oh, matrix is this array, M over here. So we don't want it to be the function itself. It's not going to run, or at least it's going to have some weird errors if we do that. So it's the result of calling that function. That's the idea. Okay, so here's where things get a little more interesting. As you know, JavaScript can do these kind of unknown functions. And we could do something like this, you know, like do matrix is assign the value of this, or like let do matrix be assign the value of this function that does all this stuff. But the thing is, we don't need to assign that the value of a variable. You know, it's like you can have the number 5, you could make like x be assigned the value of 5, but you could just have 5 on its own. It's no big deal. Not everything needs to be stored in the value of a variable. So now we have this function here, and it's kind of an anonymous function, right? It doesn't have a name. And so we can't really refer to it using do matrix, but we know that it is, like do matrix was just this thing right here. So that's basically the idea. Let me tab that over. And yeah, the idea here is that inside these parentheses, we have an entire function. We're defining this function. Before we were making reference to it, we're saying do matrix, call that, but now it doesn't have a name. It's just this function. It does all this stuff. We're declaring this function, writing it out, and at the same time, we're calling this function. So basically, matrix is actually getting assigned the value of whatever this function returns, because we are invoking the function right here. That's the main thing. So does that work? And yeah, it works. Okay, cool. So this is getting pretty nice. I'm liking this stuff, actually. This is, I think, you know, this is getting to be the best version that we've had of this so far. So let's try submitting that. We'll see if it's passing all the hidden tests. And nice. Okay, so 65 lines. I think that's pretty decent. Is there any other change we can make? Well, yeah. I mean, we're sort of using this singleton thing or closure. It's a nice thing. Like, you know, if you're not familiar with this, if you haven't done one of these before, like this is a good thing to get used to. This is a really, really cool technique. And it's one of the things that seems to be, I guess, one of the big selling points of JavaScript. A lot of people seem to really gravitate towards JavaScript for this kind of thing. Like this is one of the big advantages of the language, or at least so I've gathered so far. Now, there's something else I want to mention here. There are a few other ways we could do this. So instead of row here, we could actually just say something like this. And we've done this before. I don't know if it's really that proper, but we can say array at n. Okay, and the idea is that array at n, it's going to start out as just being an array of length n, which is what we want, except it's going to be all nulls. So we don't want it to be all nulls. We're going to fill it. Fill that with 0. Okay, so we could do something like that. If we wanted to, that would still work. We could also do like something like this, array.from, and we'll do an array that comes from basically a string of zeros, which we're repeating n times. So that'll work. We could also use an array literal to do something very similar involving a spread operator. So we can spread that out into a matrix. So it's going to take this string, which is n many zeros, turn that into an array. I said matrix a second ago. I meant array. Okay, and so that's pretty nice. What we're finding is there's a lot of ways of doing these things. I guess, yeah, I'll keep it this for now. But the main thing is, what if we want to do the same sort of thing with this, like with this outer one? So we probably could do something like let m be assigned the value of array.from, or more like this, array, yeah, let's try it like this. So array at n dot fill, and we want to fill it with these things, these rows. Keep in mind, we're just looking at different ways of actually creating this matrix right now. So let's try that. Is that going to work? And no, it doesn't. Notice it makes all of the lines the same, all the rows, it makes them the same. It's because we're not creating unique instances for each of these things. So that's sort of the problem here. Now, as it turns out, there is a way we can handle this. So I want to take this part over here and cut that out because we're going to use that again. But check this out. This is kind of strange. In fact, here, let's just do this for now. I want to show you this kind of in isolation. So we're going to say let array, we'll just make it an empty array, and we'll say return array for now. Okay, so nothing there. Now, what we were saying before is we could do like array at n, and it would just be a bunch of nulls. Another way we could do this, and I think this is really fascinating. I actually just encountered this a couple days ago, and it's pretty weird. So we have this object inside, and it's just going to be length 5, let's say. We're going to run that, and it's going to give us basically the same thing. So an array of length 5. And I could make it length n if we wanted to as well. Null, 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 length 3. So that's working. But here's what makes it really interesting. We can actually give it a function which takes a value and a key, and whatever that function returns is going to end up inside our array here. So I'm just returning the key, so it's 0, 1, 2. Wow, that's pretty cool. Now I'm pretty sure the values here are all going to be null, so yeah, not too interesting. It's more the second argument we're going to be using, if anything. And of course, I mean, this is a function. We could give it a quick little arrow function, just say value key, let's assign the value of key, and there we go. We run that, and not bad. We could also use none of the arguments. We don't need to use value or key. We could say that this just gets mapped to 5s, just 5, 5, 5. Okay, great. Or we could say that it gets mapped to this. And look at that. Okay, so that's not bad. But it kind of is bad too, because I'm only now realizing that's creating an array of like the letter 0. I don't really want the letter 0. I want it to be the number 0. So I'm just going to stick with array at n dot fill with zeros. And let's do that. And what we'll find here is now this thing, this very compact code here, you know, this one line thing here, should give us basically that empty array that we're trying to start with. There we go. All zeros over here, all zeros over here, and it's the right size. So this is kind of like that empty canvas we were starting with before. So this is doing a lot of work for us. It's basically replacing all of that stuff that we had before. Now, I guess we've kind of condensed this already. It's not what it used to be, but keep in mind it had like, there's that thing where we were creating the rows, we had nested loops, we were pushing the rows into the matrix, pushing zeros into the rows, but now we can just do this. And is it gonna work? Yeah, it's gonna work. Okay, so that's pretty not bad, guys. I mean, we got x, y, num, matrix, rotate, and place num, and that's it. That's all we need for this object. And now spiral is just this own sort of unique object. It's not coming from like the constructor of something else, because we don't really need that. You know, we're just using this one time, and it's based on some of the numbers in here, which is why it's important that it lives inside of the spiralNumbers function now. So this is kind of cool. I mean, it's got all the tools we're looking for. I like the idea of it. I like the idea that we sort of have this matrix which kind of has a mind of its own. It kind of has its own unique abilities, right? It can rotate itself, it can place numbers, and I want to do something else here. Let's actually do a little console log here of this matrix. I want to see what it's looking like at every step. And if we take a look at this, bad example. If we take a look at this, we find it starts with the 1, and then we get the 2 in there, and then we get the 3 in there, then the 4, and then the 5, and it rotates because it's hit the end there. And then we get the 6, the 7, the 8, the 9, and it rotates. And the 10, the 11, the 12, the 13, it rotates. And here's where it gets really exciting, because we get the 14, the 15, and when we get to that 16, there's nothing after that, or at least there's not an empty spot after that, so it rotates. Very nice, and it keeps the 17 going from there. So this is kind of neat. I think this is a really interesting way of doing it. I hadn't thought of this one before. But the thing is, I don't think it's very efficient. You know, like, we're doing all these rotations and stuff, but it is kind of overkill, you know? We don't really need to be doing all those rotations every time. It feels a bit excessive. I mean, it's not bad on the memory, but I don't think it's going to be great for the time complexity. Okay, and then, yeah, we get to the end here, and we say, oh, okay, rotate that back into place, and everything is good, and everyone's very happy. Let me delete that, and we'll just submit this, and good. Okay, so that's all submitted. Let's, we're going to focus on the code part of the window here. We're going to copy this whole thing and we're going to paste this in. Now, normally I would just sort of comment all of this out, but I'm trying something a little different now. I'm going to say spiralNumbers 1. And now that's going to be fine, you know, it's not going to interfere. This is not the function it's looking for. So it's just like, oh, okay, you got some extra code down here. That's fine. I'm okay with it. So I'm just going to keep that down there. I don't know. Do we need a comment for that? It probably speaks for itself. Okay, so we're going to try this a bit differently. In fact, we're going to use a more traditional approach to this. So we're going to look at this in sort of the... I don't want to say the more obvious way, because I wouldn't say that this is going to be particularly obvious what we're going to do here, but I guess the more common way of looking at this is what I'm trying to say, like the sort of the approach that you would normally see people using for this. All right, so basically the idea is that now instead of always moving to the right as far as we can and then rotating the matrix whenever we need to, instead of that, now we're just going to go in the direction that we have to. So basically we're going to start by going to the right, then we're going to go down, then we're going to go to the left, then we're going to go up, then we're going to go to the right, and we're just going to keep that happening over and over again. So basically the way we're going to handle that is we're going to say let directions be assigned the value of this array, and technically it's going to be kind of like a matrix. It's going to have 4 directions in it. Okay, and when I say directions, I mean sort of like an x, y value, an I and j value. So the x value is going to represent the rows, the y value is going to represent the columns. We want to move to the right first, so that's 0 in the row direction, 1 in the column direction. Then we want it to go down rows and not change columns, so that's 1, 0. Then we want it to go to the left, so we want to stay on the same row, but we want to de-increment the columns. Finally, we want to de-increment the rows and stay on the same column. So basically, these directions are left, down, right, down, left, up. Those are directions. Okay, and then how are we going to cycle through these? Well, basically the idea is we're going to say direction index is going to be assigned the value of 0, and we're going to do something where basically instead of rotating, when we want to change directions, so I'll just make a comment for this and we'll just do something like this. If we want to change directions, we're going to say direction index is assigned the value of whatever direction index was plus 1, and then at this point you're maybe thinking like, well, why not just do a direction index plus plus? It's because we want to do a mod 4 at the end here. Why mod 4? Well, basically because we want these to repeat. We want it to go right, down, left, up, right, down, left, up, right, etc. And so basically the idea is that after it gets to the end here, once the index is 3, we want to increment it. It gets to 4, that's off the array here, that's going out of bounds, but we mod for that and it goes back down to 0, which is exactly what we want. Okay, and we're only incrementing like to the right. We're not going like, we're never going to do direction index minus 1 because that would be the wrong direction. I mean, keep in mind, we're only turning clockwise every single time here. Okay, so that's how we're going to change directions. I'm actually going to, not do that for now because we don't know when we want to do that yet. But anyway, those are going to be our directions. Now we should probably get a matrix in here. So let's say let matrix be assigned the value of, I don't know, how do we want to do this one? Do we want to do something like what we had before? Like do it sort of the old-fashioned way like this? I don't know, it's up to you. I'll just bust this out for now. Matrix.push row. And we want our for loop in here for let j be assigned the value 0, j is less than n, j plus plus, and we just want to do a row.push 0. That's what we're starting with. And yeah, that would be our matrix. So I think that's working. I think it's fine. Let's just make sure of that. So matrix, there we go. Great. Yeah, that one's looking good. That one's looking good. I think we're okay. I think this is working the way we wanted to so far. Okay, so what do we want to do next? Well, basically, okay, what do we know about this? Well, we know that there's going to be at least 3 elements here. So, I mean, even if this was a 1 over here, we're pretty much we're going to be reassured that matrix at 0 is going to be a thing. It's going to be a thing. So we're going to put our 1 there. It's going to exist. And we also sort of want to have the x and y that we had before. It's not going to be this.x and this.y anymore. It's just going to be x and y, and they're both just going to start at 0. And it's just going to represent our current position, and it's what we're going to change using these directions here. Okay, so instead of, well, yeah, eventually we'll want to return the matrix. So we're starting with this, and then I'm going to say for let num be assigned the value of 2. Num is less than or equal to n, num plus plus, and then basically we're going to do some stuff in here, but I want to make sure that this is making good sense first of all. So starting at 2, because we've already laid down the 1. Okay, cool. So then basically, why did I start with this? Well, it's because I want this loop to sort of look for the next element as kind of a first step. There are other ways we could do it, but let's do it this way for now. So we want to take dx and dy. And check this out. I want to show you all the steps here. So we're going to say let dx be assigned the value of directions at direction index. Direction index. Yeah, directions at direction index at 0. And let dy be assigned the value of directions at direction index at 1. Okay, now that's a mouthful right there. Maybe we can clean that up a bit. We're going to use a destructuring assignment. So we could say, let dx and dy, we can assign them at the same time. And, we could say like, direction, not direction index, directions at direction index at 0, and then directions at direction index at 1. Okay, so is that looking much better? Not really, to be honest. I mean, it's actually looking a little more crowded. So what is this thing, directions at direction index? Well, it's basically one of these. So directions has a bunch of these little 2-element arrays. So directions at direction index is one of these things. Maybe it's this one, maybe it's this one over here. But it's basically a set of 2 elements, or an array of 2 elements. So because it's an array of 2 elements, directions at direction index at 0, followed by directions at direction index at 1, that is what this thing is. I mean, it's just the 0th element and the first element. So that means I don't need to put this in an array. I don't need to put the 0 and 1. That's it. dx dy is this matrix right here, or this array, sorry, right here. It's just going to be, let's say if this one was, let's say the direction index is 1, so this thing right here is going to be 1, 0. So this is just going to say, okay, so dx is 1, dy 0. Done. So that's nice. That's really showing us sort of the power of these destructuring assignments, which is pretty cool. Okay, so we've got that, and then we basically want to say let next x and next y be assigned the value of x plus dx and y plus dy. Okay, so we're basically just saying whatever the x value was, we're adding on this change. And then whatever the y value was, we're adding on this change. Okay, so basically that's the idea. And then we want to say, okay, so this next x and next y here, we want to check a few things about it. So first of all, is next x in the matrix? Is it within range here? And also, is next y in the range of the columns, which is why I'm doing at 0 there. I could also do at x or at next x or at something like that, but what if next x isn't in the matrix? Well, okay, the answer to that is it wouldn't get that far, so we don't need to worry about it, but Anyway, the point is matrix at next x at next y. Now keep in mind, it's not going to get to this point if these aren't already both true, so we know this isn't going to throw an error and say, hey, you can't find property 0 of undefined or something like that. And then we need to say, okay, if this is 0, and we need just a little bit more room in there. Okay, great. So if this, then that basically means we can move into the next spot. So we can move into the next spot. So let's do that. We'll say matrix at next x at next y is assigned the value of num num plus plus, we're going to increment it. And then we're going to reassign x and y. We're going to say, okay, so now x and y is going to be our next x, next y. Because they're not really the next ones anymore, they're the current ones now. But if that's not possible, if you can't move into the next spot, if there's either something there, or if you've reached the end of the array, if you're going out of bounds, well then we want to rotate or change direction. Clockwise. Cool. All right, so change direction. How do we do it? Oh, we already know. It's using this thing over here. So we're going to grab that. We're going to put that in here. We're going to get rid of this. And let's see, is there anything else we need to do here? Did we miss anything? Let's find out. Let's try running this thing. And what we find is that we get that far. 1 and 2. Okay, I think part of the reason is we're saying num is going from 2 to n. Well, keep in mind, n here is 3, so, that's not that much. Let's do this, okay? So n times n, I think that's more what we're looking for here. And okay, 1, 2, 4, 7, 9. That doesn't really look like it's working the way we want it to. So, why is that? Let's investigate here. So, are directions correct? Yeah, they look correct. I think our matrix was good from the beginning. We start with an xy value of 0, 0. We fill in the 1 in the first spot there. And then for each of these, we're saying dx and dy are going to be our new directions here. Next x, next y is what we get by adding those parts on. We want to check if the next x is in the matrix, the next y is the possible value for the column, and we want to make sure that matrix at next x, next y is 0. And if that's the case, then we're going to say, okay, so it's 0, we're going to make it num. And then we're going to increment num, and then we're going to say x and y is next x and next y. And if that doesn't work, if we're not able to do that, we're going to change direction. Okay, so I guess the question here is, well, it's not working. What's going on here? What's the problem? So, okay, maybe we can do like a console log or something like that. Let's see, console.log, matrix. We'll see what's going on with each of these, what it looks like at each step of the way. So, okay, 1, 2, it's not even really putting in the 3, it looks like. What's going on with that? Oh, you know what? I think this might be the issue. I'm doing a num++ up here. I'm also doing a num++ down here. I actually don't want to be incrementing num if we're just rotating, right? So because of that, I'm not going to include both of those pluses. Okay, so let's run the test now, and hopefully that resolves the issue. It did. Okay, so a console log is always a nice helpful thing if you want to really get in there, look at the guts of it, do a bit of debugging. Okay, so that's good, right? It seems to be working. There's one change I'm going to make, which is this. Check it out. We're assigning the value of num, and then we want to increment it. We can do that sort of in one step here. We can just do it like that. And yeah, that's pretty not bad. Okay, so let's try submitting that. Let's see if that's going to pass all the hidden. And yeah, it does. Okay, so there are lots of variations on this. Like we could do this in different ways. Like for example, here I'm assigning the first value, and then I'm starting with the second one, and I'm sort of like finding the next possible index, just laying down the value if we can. We could do this in a different order. Like we could say, first lay down the value, then find the next thing. Like if you can, otherwise rotate it. So we could make it a little more like what we had down here, but variety. So this one is a bit different. This is where we're kind of assigning or finding the next index first, then placing the value if we can, otherwise just rotating. And that's kind of cool. It's kind of not bad, but it does mean we have to sort of assign this value at first, which means it's one more thing to worry about, I guess. Anyway, I'm not too concerned about that. I think this one looks good. I would say this is sort of the most typical implementation for this challenge here. So this is what you'll see. I mean, like I was saying before, this is a pretty common problem. Like if you search on the internet, you can find this problem in other contexts, and there's some variations on it too. Like sometimes maybe you start in the middle here and then rotate outwards from there, like the 1, 2, 3, 4, like that kind of thing. So yeah, there are variations. Anyway, if you do look this up, go on like Rosetta Code or something like that, and you're looking for other solutions to this, probably this is going to be sort of the style of solution that we're going to find. So we're probably going to have something with like with our directions here, where we're incrementing our directions. That's a pretty typical way of solving this one. Okay, so from what we're looking at, this first one here with the rotating, it's fun, it's neat, it's kind of cool to think about. It's kind of overkill at the same time. Doing that whole rotation thing, it's more than we need to do. Whereas when we look at this one over here, it's a little bit tighter. It's nice, it's just going through, laying them down one at a time, starting with a matrix of all zeros. And it's getting the job done. Both of them are getting the job done. I think probably if I had to take a guess, I would say the second one here is a little more efficient. But I'm wondering if there's a more efficient way still that we could do this. So I want to start a new one of these. So I'm going to copy, paste that in, and I guess we'll say this is going to be spiral numbers 2. We've got spiral numbers 1 down there, and yeah, this shouldn't affect anything really. So I'm going to delete a whole bunch of stuff here. So we're just going to have this part here, just returning the matrix. And yeah, it's just zeros now. I mean, what did we expect? Of course, just zeros. So, okay, here's the idea. What we want to do now is, okay, and this is sort of the thing. I was looking at this and I was thinking, we want to make this spiral matrix here. We want to fill in all these numbers, but if we think about the way we're doing this, it's kind of like, we're creating this empty matrix. We're creating this thing that's just all zeros. We're going through it. We're doing a double loop here. We're incrementing through all the rows, all the columns. And then the problem starts. Then we go through and start to fill in this stuff, and you have to worry about like direction indices and rotating and all that kind of stuff. And so I was looking at this and I was thinking, well, could we just do all of it right here? Like instead of pushing a 0, could we just find the value that we need and push that in instead? And let's get a bit more space in here. So that basically we're not creating the matrix with all zeros and then filling in the numbers after. Instead, what I'm proposing here is basically we just create the matrix. And that's it. So the question is that possible? Is there like a mathematical formula we can use to come up with all these things? It seems kind of tough. It seems like it's not necessarily going to be possible. So let's investigate that. That's going to be our next thing here. So let's just get rid of what we have over here, and now we're going to, I guess, reposition this. Basically, what we want to do here is we want to take a bit of a different perspective on this problem. So the first thing I want to point out is basically we can sort of think of this as having like levels, like layers, like depths. So let me show you what I mean by that. So, oh yeah, I've got this marker tool now. This app, it's getting pretty damn good. Pen size 5, hopefully that's big enough. So the first layer is kind of like if we start at the 1 and we're just, as we go to the right, we're increasing the numbers. As we go down, we're increasing the numbers. I mean, that one is pretty straightforward. The next one, we're starting at 25 here, and we're just incrementing the numbers. And we basically just have, like, depending on the size of the matrix, depending on our n value here, we're going to have a particular number of these depths. So, like in this case, n is 7. We basically have 4 layers, 4 depths that are possible over here. Now, the reason I wanted to identify these, first of all, is because we can sort of look at these and notice some patterns about them. So first of all, we can say, all right, well, if we start here, and let's say we're just going to be looking at this particular depth, so it's not like we're going to wander into any of these other depths here, so just staying with this kind of yellow outermost one here. Basically, we're starting at 1, and then if we increase j, if we go to the right, we're increasing j, that's just increasing the number by exactly that. So this is like 1 plus j, 1 plus 0, that's 1. 1 plus 1 is 2. 1 plus 2, 3. So basically, 1 plus j is giving us all the values we're looking for over here. But then we get down to the end over here, and we're finding, well, now j is not changing, but now I is changing. And notice I and j don't change at the same time. Here we go strictly to the right, strictly down. So if I increases, the number increases. If j increases, the number increases. Okay, so that's pretty neat, pretty nifty. That's pretty special. Pretty not bad. And so basically the idea is the distance we're traveling from this starting number here, whether we're going to the right or down, it's increasing the number by 1. So what I'm trying to say is basically this. Let's get this back to a reasonable size. Come on. We've got this number here, right? We've got the 1, and then basically we're just increasing I and j will both increase the number. So any number you want to find that's of this depth is just going to be 1 plus I plus j. That's it. But is that going to hold up for these other layers as well? Here, we're starting with a 25. So we're going to have to figure out how we get that 25 in just a sec. We'll talk about it, don't worry. But the main thing is that we're starting with a 25, and then, again, increase j, you increase the number. Increase I, you increase the number. And those are the only things that are going to affect it. The thing is, now, it's not like I and j are both 0 here, right? So we sort of want to say like j would be 0, 1, 2, 3, 4. I would be 0, 1, 2, 3, 4. So it's not so much like I and j we're looking for. It's kind of like I minus the depth, j minus the depth. That's kind of the idea. So we have this idea of depth. Okay, let me start jotting this down. So we're going to have something like start. Okay, our numbers are going to be our start value. And when I say start, I mean like the 1, the 25, the 41. And then we're going to add to that our differences here. So it's going to be I minus, I'll say d for depth, plus j minus d for depth. Okay, so that's basically the idea. We can get pretty much any of these values, anything from this half, or I guess that's technically more than half of the matrix, we can get using this kind of formula. So this part, we've got it. Well, we should probably talk about how we can find depth. So what is depth? Well, anything that's on this outer level here is going to have a depth of 0. Anything on this next level is going to have a depth of 1. This would be depth 2, depth 3. So basically the idea is we kind of want to find like our outermost index here. Like basically you'll notice all of these numbers have a 0 in sort of some form, like these, it's basically our I value that's 0, 0, 0, 0. And then over here, our j value, well, it's not 0, but it's right at the end. So it's kind of like n minus 1, I guess, right? So n minus 1 minus j would be 0. So basically the idea is what we want to do for our depth is we want to find the minimum of I, j, and then n minus 1 minus I, and then n minus 1 minus j. Okay, and if you're wondering about this, like why it's the minimum of these 4 values here, well, these 4 values kind of represent how far from the edge we are, right? I represents how many units from the top are you? J, how many units from the left are you? This over here would be how many units from the bottom are you, and this is how many units from the right are you. So if we get the minimum one of these things, that's the depth that we're on. So like, let's just take like, I don't know, this one at random, let's say. What would that be? 0, 1, 2, 3, 0, 1, 2, 3, 4. Okay, so that's 3, 4. I value of 3, j value of 4. So, and n is 7 here. So basically 6 minus 3 would be 3, 6 minus 4 would be 2. This is 3, this is 4, so we have 3, 4, 3, 2. The minimum from those would be 2, and it turns out this one does have a depth of 2. You know, it's like this would be 0, this would be 1, this would be 2. So this seems like it's working. So we've got our depth, it's going to be the minimum of these 4 values, and then what we're going to, like what our actual value is going to be for a given I and j, because, I mean, we are going to have I and j here, that's the idea. So basically the idea is that, yeah, our number for the given I and j, we're going to find the depth, and once we found the depth, we're going to say, take that start value and then add I minus d plus j minus d. Okay. How do we find the start value? That's the question now, right? So we want to know, how are we going to find this 41 here? How are we going to find the 49 here? How are we going to find the 1? How are we going to find the 25? So let's talk about it. I guess I'll make kind of a t-table here. So there's the depth, and this is going to be the start value. Okay, so for a depth of 0, 1, 2, and 3. I'm sort of trying to make it line up over here, but basically the idea is that for a depth of 0, we're just starting at 1. It's nothing more complicated than that. We're just starting at 1. So that one, not super difficult. Now, if we want to think about how we got to the 25 here, well, we're starting at 1, right? We're starting here, and then we have to go around like one full rotation and then get to the 25. So how many units is that? Well, there are 7 in each row, 7 in each column. So we've already got the 1 here. That means we need to go 6 more units to get to the end here. And then we need to go 6 more units from there to get down to here. And then another 6 to get here. And then 5 to get here plus 1 over there, so another 6. So basically 4 times 6. 1 plus 4 times 6. That's the idea. Okay? And well, 4 times 6 is 24, so that's 25, which, yeah, that's the number we're looking for. So that's good. And then when we look at this next one, okay, so we've got the 25, and then from the 25, we've got to go 4 units this way, 4 units this way, 4 units this way, 3 units here plus a 1, so another 4, so 4 times 4. So we basically have 1 plus 4 times 6, plus 4 times 4. And I just want to jam out with that for just a sec. Yeah, we're good. Whoops, pen tool. Okay. This is the same as, first of all, it's the same as 1 plus 4 times, oh, that was meant to be a parenthesis, 4 times 6 plus 4. In other words, 4 times 10. Well, 4 times 10 is 40, so this must be 41. Is 41 correct? Is it the number we're looking for? Yeah, it is. Okay, cool. So that's good. Now let's switch back to this. We want to look at the last one, and it's basically going to be 1 plus 4 times 6 plus 4 times 4, like we saw before, plus some other thing, which is specifically going to be, well, we're here, 2 units this way, 2 units this way, 2 units this way, 1 plus another 1, that's another 2 units, for a total of 4 times 2. So I'll put that in here, 4 times 2. Okay, cool. So we're maybe noticing a bit of a pattern in here. So just to get a little bit of extra room, this is going to be the same as 1 plus 4 times 6 plus 4 plus 2. Okay. So that's basically the idea, and then that's going to give us 49. It's the value we're looking for, so that's all good. The thing is, we're still looking for a mathematical formula. This looks like it's getting us closer to that, but it's like the main thing is we've got the 1 plus 4 times something, 1. 1 plus 4 times 0, technically. 1 plus 4 times 6. 1 plus 4 times 6 plus 4. 1 plus 4 times 6 plus 4 plus 2. So basically, what's going on in the inside of the parentheses here? If we can figure that out, then we have a formula. It's basically just 1 plus 4 times whatever this number is going to be. So the question is, well, what's that number going to be? And if it's going to be something like this, well, where's the 6 coming from? Well, it's the fact that we had 6 other units in the row aside from just the 1 here. So it's basically n minus 1. So we sort of have like n minus 1 plus n minus 3 plus n minus 5, as sort of as large as we can here. So basically the idea is this. If we have an n, yeah, that's good. We have an n here. And I guess I didn't really leave a lot of room, so let's section that off there. Actually, wait a sec. Hold on. They've improved this app, right? So does that mean I can move stuff? Can I just like select? Oh, you bet I can. Okay, so did that select it? Is that good? Can we move it? Oh, wonderful. Okay, so that's great. Exactly what I was looking for. We'll go back to the pen and move this over and go back to the pen again. Okay, so actually, you know what? Here, let's get that n out of there. That's kind of sloppy looking. All right. Sorry about the suspense here. There's n, and basically we want to say for depth that's, or not n, let me get x. How about that? Yeah, x. Because n is already taken. N is something that already exists. So we're going to say this is going to be 1 plus 4 times, what's inside here? Well, it's going to be n minus 1 plus n minus 3 plus n minus 5. Kind of etc. in there, right? So let's simplify this. Basically, let's take a look at these. Let's take a look at those in isolation, I guess. So basically, what we could say is, okay, what's our x value going to be? We'll start with 1, and then we'll do 2, and then we'll do 3, and we're going to look for some patterns here. So that number we were looking for, we had n minus 1 to begin with. That's not going to get much simpler. Then we had n minus 1 plus n minus 3. We can simplify that one. That's the same as 2n minus 4. Okay, and then we look at this one over here, which is going to be n minus 1 plus n minus 3 plus n minus 5. And when we simplify that, that's going to sort of reveal a bit of a pattern here. It's going to be equal to 3n minus 9. Basically, the idea is this. If we want to come up with like a rule for this, it would basically be that we have x times n minus x squared. Okay? So another way of doing this whole thing is, whatever our x is just going to be x times n minus x squared. So just to clarify that, if x is 1, well, 1 times n is n, 1 squared is 1, so it's n minus 1. If x is 2, we would have 2n minus 4, which is what we have. If x is 3, 3n minus 9, which is what we have. If x were 4, I'm going to go ahead and guess that we would have 4n minus 16. Okay, so because we can represent this as x times n minus x squared, let's do that over here. And in fact, you know what? Here, let me change this again just a little bit. Not x. And I'm going to get rid of all this stuff. I'm just going to make it d. Because that's what it's supposed to be. That's what we want, right? So let's switch back over to the pen, and we'll say for depth of d, the start value is going to be 1 plus 4 times d times n minus d squared. Okay? And that's just grabbing from this over here, which we found. Yeah, that was the full derivation. Okay, so there we go. That's what we're getting. That's our start value. So we have an expression for the start value now. Check it out. So over here where we said it's basically, actually, you know what? Let's zoom out at this point. So over here we're saying start, like our value here is going to be start plus I minus d plus j minus d. So kind of like, okay, start is the 1, the 25, the 41, the 49. This I minus d is how many units are we going down from that start value? And then the j minus d is how many units do we go to the right from that start value? And we know start now too. It's 1 plus 4 times d times n minus d squared. Okay, and of course d is this thing over here. So here's the thing. I didn't say this is going to be an easy formula, but it's a formula nonetheless. We're getting something. The problem is we're only getting something for this upper triangular part of the matrix, or yeah, it's an upper triangle anyway. It's not the traditional one necessarily. Or wait, yeah, it is. It is. We're good. Okay, so anyway, the point is, I'm going to switch to marker over here. Let's size that up a little bit. And let's switch colors. So the question now is, what are we going to do with the other half? These are tough to pinpoint. Okay, so we're going to start over here and go up. So that's like the outermost depth for the bottom triangle. This is depth 1 for the bottom triangle, and this would be depth 2. And then, actually, I'm not happy with that. Let's retry that. Good. And then this would be the same. You know, there's not going to be any difference for that one. Okay, so let's switch back to the pen now in the size of 2, and going back to this. So how are we going to look at these bottom ones? We're not going to be able to follow exactly the same formula as up here because it's a little bit different. You'll notice like now we're starting at the 14 down here, and it's kind of like we're subtracting the values each time. So we could do that. You know, we could come up with a new start formula to find the 14, the 34, the 46, or like the 13, the 33, and the 45. But that's fully possible. We could do it that way, and then basically add to it kind of like the opposite of this. So like n minus 1 minus I plus d, or something like that, you know, something that would give us like how far to the left and how far up are we moving from this value. That's all possible. We could do it that way, but I don't wanna. I want to do it differently, and there's a reason for that. So I want to start with this value and then basically de-increment, right? So instead of them going from here and then going up, I'm going to start here and they're going to go down. So basically I'm going to take our start value and I'm going to subtract. I'm not going to add I plus d, add j plus d. I'm going to subtract I'm not going to add I minus d or j minus d. I'm going to subtract I minus d and subtract j minus d. I'm going to get rid of those. Basically, how far are you from this number? That's what I'm taking away. The thing is, keep in mind, now I minus d actually doesn't tell us the distance from this number because we're not starting at 0, 0. We're starting at 1, 0. So by the time we're here, I is already 1 and d is 0 here. So like this would be 1. We've already moved 1 unit away. So we should already have d incremented 1. So it's not that we actually want to start at 24. It's that we want to start at the next one, which conveniently is 25. And we already have the formula for coming up with 25. So we can actually still use this, except it's basically going to be the next one. So it's not going to be the start at d, it's going to be the start at d plus 1. That's going to be sort of the idea here. And then from there, we're just going to subtract these differences. So that's the game plan. That's the idea. So let's get all that down here. So first of all, we've got this function. It's called start. It's how you're going to find the starting point, and it's for an input of d for depth. We might as well just call it depth, actually, just to be clear. Now that I'm typing, it's a lot simpler. Writing it out with a mouse is, yeah, it's a pain. It's a pain. Anyway, okay, so what are we doing with this? Start at depth. Well, basically, I think we found that it was 1 plus 4 times depth times n minus depth squared. Now we could do like one of these for the squared, but instead I'm just going to do depth times depth because I've heard that it performs better. It's a little faster, you know, on the level of milliseconds, but milliseconds make a difference in the long run. So okay, that's our start depth, and let's just try this out. So let's return start at, I don't know, 1, let's say. And it's saying 9. Yeah, it should be a 9 there. Okay, that makes sense. In this case, 17. Well, yeah, it should be a 17 there because that's a depth of 1. That's where it's starting. So good. Okay, so that's working good so far. And then basically what we want to do for each of these things is once we get in here, we basically want to say, well, first of all, let difference. So the difference is going to be, well, hold on, where are my manners? We need to find depth. We don't know what the depth is yet. So it's going to be math.min of, like we were saying, I, j, n minus 1 minus I. Oh, that's supposed to be a 1. Whoops. And n minus 1 minus j. Pretty sure that's what we had, right? For our, yeah, good. That's looking good. And okay, so we've got our start formula. We've got our depth formula here. Now we want to let the difference, okay, and when I say the difference, I mean basically these two parts here. So the I minus depth and j minus depth, and we're going to add those together. So it's going to be I minus depth plus j minus depth. There we go. Great. And I probably shouldn't have that semicolon right in the middle there. That might mess with things. Okay, so what do we want here? Well, I guess we just say let num. Yeah, we haven't used num before, I don't think, in this one. Okay, so num is going to be equal to, well, what's it going to be equal to? That depends. It depends what part of the matrix we're looking at. So is it the part where j is greater than or equal to I? So in other words, this upper triangular part? Or is it the part where j is less than I? So in other words, the lower triangular part. So let's try to figure that out. Basically, if it's the upper triangular part, then we're basically going to have start at depth plus difference. Yeah. And otherwise, start at depth minus difference. Let's get that on the next line, and let's try that. Oh, and we don't want to push 0. Instead, we want to push num. So what kinds of values are we getting? Well, if we look at the upper triangular part, it's actually good. 1, 2, 3, 4, 5. We've got the 9 in there. If we look at this part, 1, 2, 3, 4, 5, 6, 7, 8, 9. The 17, everything from there is good. The 25 is good. The lower triangular part of this is atrocious, though. It's not starting at the right value, because notice it's starting at 1 and then it goes to 0, negative 1, negative 2, negative 3. It should start at 17 there and then go 16, 15, 14. So that was the problem. Remember, this out here is a depth of 0, but we're starting with the start value at a depth of 1. So we need to actually increase the depth here. We'll put a +1 on that. We'll run it. And there we go. Look at that. I have to say, this to me was a huge victory. Being able to, well, okay, let's not get ahead of ourselves. Let's make sure it passes all the tests. Great. This is a huge victory to me because, I mean, I can't think of a more efficient way we could do this. Okay, and that might sound silly considering how long it took to actually come up with all this stuff over here. But the main thing is, once we know those formulas, like, we're not creating a matrix and then filling it in with stuff. We're not keeping track of like which direction we need to move in. We're definitely not doing any of this big object stuff. We're not rotating any matrices. As we're creating the matrix, every value we put in is the final value and it's in the right spot to begin with. This is a beautiful way to create a spiral matrix, in my opinion anyway. I mean, you might prefer one of the other methods and that's fine. But me, I like this one. Okay, now I was thinking about this and I was thinking like, this is cool. I think this is really nice. I like it a lot. But you know, when you love something, you got to set it free. So we're going to get rid of that one and we're going to sort of start a new one, but it's going to be the same thing. I just want to, you know, because I was looking at this and I was thinking, wow, we can really make this very efficient, can't we? And I thought that's pretty neat. I wondered just how efficient we can make it. And so I started to get into this and I got a little bit carried away, but I did find a way to make this like pretty not bad. So first thing I'm going to do, I'm just going to clean this up a little bit. So I'm going to keep the j is greater than or equal to I. And by the way, when I say clean it up, I don't necessarily mean in sort of like the good way that we're used to. I'm just going to express it a little bit differently, I guess. So how should we do this? Basically, okay, just to sort of tighten it up, instead of doing difference over here and instead of doing start over here, I'm just going to handle all of this stuff right in here. And for depth, we're going to shorten the name because we're trying to see how short we can make this thing, just, for fun. Okay, and what do we have in here? Basically, it's going to be, what was it? 1 plus 4 times d times n minus d times d, right? And then from there we had plus I minus d plus j minus d. Yeah, oops, there we go. Okay, cool. That's what we're looking for. And then for the other one, okay, basically, well, okay, we can sort of simplify it. I mean, we could write it like the same sort of way as what we have up there. So, except with a d plus 1 inside here. But we could sort of simplify it actually. We could say 4 times d plus 1 times n minus d minus 1. And if anyone wants to see like the proof of that, the derivation of that, let me know. We can talk about it. And we're going to subtract I minus d minus I minus j minus d. Yeah. Okay, so that way we don't have any like start. We don't have any difference or anything like that. We're just handling the whole thing right here. And is it still working? It is. And in fact, since we're handling all that right here, I mean, that's what num is, right? So we could just replace this thing with, yeah, that. So let's get rid of that. Don't want to get rid of that. Let's do this. Okay, so we'll run the tests on that. Okay, that's pretty cool. So now this is our row, right? So could we... Okay. You remember when we were looking at that thing earlier when we were like, let array be assigned the value of array.from with an object that just contains a single property, which is length, having a value of n, and we found that we could take the value in the key here and kind of map it to just like something involving the key. Okay, so what I'm going to do here is something a little bit sneaky. I'm going to say function array. So we're going to have this function, it's called array, and it's going to take in a function. Okay, so we're going to call that func. This is maybe going to seem a little weird, but I'm going to say return, and it's going to return basically just this thing, array.from length is going to be n, so it's going to keep that part in here, and then it's basically just going to say the value and key here, it's going to get mapped to function, the input function here, with an input, with an input of k, func. Okay, cool. And then basically from there, well, how's this thing actually working? Well, let's say return r, and our function is going to be something that just takes our index and returns that index, first of all. So 0, 1, 2, that's what we're looking for. This is going to go all the way to 4. Good, that's what we're looking for. And then let's switch this up a little bit. So basically, instead of just I, let's say we want to map it to I times 2. That's basically the idea. Yeah, it's 2 times the thing. The nice thing is this is giving us the index of the array. So what's cool about this is it allows us to basically rework this. So instead of doing all this stuff, we could just say row is going to be an array, and the function it's going to take in is something that takes j to all this, just this number right here. And I don't think I need the parentheses on that. There we go. So that's going to be our row, and we don't need that closing brace anymore. Let's run that. And it doesn't work because it's like, hey, what are you talking about? D is not defined. So we do need to have our value of D in there. I got ahead of myself here. So let's say J goes to this thing, and instead of row.push, we're just going to say return that. Yeah. And we need to close this up. So is that going to work? Is that better? Yeah, that's better. Okay. Now, that's looking good, but there are a couple things I want to change about it. So first of all, we're looking at this. It's basically taking our J value and mapping it to all of this. And we already know what I is from the outer loop here, but there's one change I want to make. This is kind of strange. This is something I wasn't familiar with, and actually I'm still not very familiar with. I didn't even really know how to search for this to make sense of it, but as it turns out, there's a way we can do this for these arrow functions. Like, you know, we've seen situations before, like over here, where an arrow function takes two inputs and they're in parentheses, they're like a tuple, and then it just maps to this thing over here. If there's just one of them, we don't need it. We can just, like the J over here, you know, it doesn't need to be in parentheses. But what's really weird is we can actually put our outputs in parentheses as well, and basically say we want this as our first output. And then as our second output, we want this whole thing. So let's grab that, put that in, get rid of this stuff over here, get rid of this stuff over here. And do we have the right number of parentheses? Let's find out. Yeah, that works. Okay, cool. The spacing is getting a little weird here. Let's just do that, I guess. Okay. So it's getting a little strange, but it seems to be working. We've got this D value here. We've got this other thing, which is ultimately the number it's returning. But again, we did this to avoid a loop, right? But now we have this other loop on the outside here. So instead, we could just say, well, matrix is going to be an array. And it's going to be an array that has an index. What does that index map to? Well, it basically maps to this thing, right? This row here. So could we just take that, paste it right in here? Would that work? I wonder. So let's see. Let's run the tests on that. And yeah, that works. Okay, so this is getting pretty compact here. I mean, especially when you consider what we started with down there. Return matrix, let matrix be that. Why not just return that? Yeah, take that whole thing, return it. Okay, still working. That's pretty cool. And then, you know, we've got this function up here, but really, I mean, we could define it as an arrow function as well. R is something that takes a function and it just returns that. So that can be sort of a one-liner as well. We run this and we find, wow, yeah, that's getting pretty compact. But check it out. Even this thing could be an arrow function too. So even this, we could do something like this. Right? Make it an arrow function. But like we saw before, in a situation like this, we can make it a tuple, sort of like we were doing, well, like we have right here, you know, with this D value and then the other value. So we're going to do the same thing. We're going to say array, this function is going to be our first value up here. So we'll paste that in. We'll put in a comma. And then on the next line, this is the thing we're returning, right? So let's just take that whole thing and we'll put it in there. And okay, so this is getting a little weird looking. So maybe we can space this out a bit better. Okay, and maybe these guys should, you know, do something like that. That's probably good enough. Let's run the tests on that and look at that. So that's really all we need. I mean, this is our spiral numbers. If we were trying to do like a code golfing challenge here, we could even shorten this to just be the character A. And now, like, aside from, you know, modifying this, making this like just an F, this is like, I don't know if that could really get much more efficient than that. Like, that's pretty good. We don't have the character counter here, but I would imagine it's not too many. Is it passing all the hidden tests? Let's find out. Yeah, it is. So basically, spiralNumbers 3 here, it's doing the same exact thing as all this, except we're just putting it into this weird functional looking notation which is, yeah, pretty strange. Anyway, compare this right here to what we started with. If we take a look at our very first attempt, like this went on and on and on. This was like, what was it, like 60 lines or something like that? It was a lot. So we've economized a lot of lines. This is really not taking up nearly as much space. I think it's working more efficiently too. I think what we found before is that this exceeded the time limit for our first algorithm, but now it works. So it didn't have any difficulty coming up with a 1000 by 1000 spiral matrix. So that's pretty amazing. Now it did exceed the output limit, but it didn't exceed the time limit. That's the main thing. Okay, so anything else to say about this one? I don't know. I feel like we covered a lot of ground here, so let me know if you have any questions, comments, or concerns or anything like that. And yeah, have a great day. Remember to keep believing in yourself. Did I submit this one? Let's just make sure. Yeah, okay, we're good. So